Once again, the recordings are going to be from this point forward posted in the modules, and you will not need a passcode to view them. So today we're going to be covering chapter 17, and also we'll be having a quiz for last week's topics, which was chapter 14 and chapter 16. Again, we'll have that a little bit later, around 2:50 or so. I think I set that up for the time for the quiz. And that'll be quiz number 6. So we have 3 more quizzes after quiz number 6 for the semester. All right. So let me share the PowerPoint, this week's PowerPoint. All right. So this hopefully you can all see this particular chapter is going to basically talk about some of the reasons why our probability estimates can be influenced and can be different from the relative frequency calculations that would be the exact probabilities. So that's what we're going to talk about today. Hopefully you'll find it somewhat interesting. So let's get to the slideshow. And again, we'll start off with some thought questions here. It says here, do you think it's likely that anyone will ever win a state lottery twice in a lifetime? Well, if you do follow lotteries, you should be able to answer this question.
No.
No? Okay. Anybody who follows lotteries, Well, the answer is yes, it's happened. It's happened a few times. And we're going to be dealing with this particular idea that even though it's a very low probability that one particular person would win twice, maybe they submitted the 2 lottery tickets and they at different times and they won both of them. Over time and throughout the population, it can happen that more than one person wins. Right? And this is not as unlikely as you might think. How many people do you think would be needed? Now, this is an actual famous probability question. It's called the birthday problem. Let's see if anybody can guess something about this. Well, maybe somebody knows the answer. But it says, how many people do you think would be needed in a group in order to be at least 50% certain that at least 2 of them will have the same birthday? When we say the same birthday, we mean, of course, month and day, not year. Does anybody have any idea how many people it would take to be in a group?
Maybe 30 people.
30, okay. Anybody else? Nobody else has any feelings about this?
At least over 365, one for each day of the year.
It's a very safe answer. All right.
Is it like 50 people?
50. All right. So we have 30, 50. And did you say at least 365 or 365?
At least.
At least 365. Okay. So I like your answer. But there is a definite answer. We'll find out about it a little bit later in this slideshow. There is an answer. And you can mathematically calculate it. Although it's not required for this course to know how to do it. Sort of explained. All right. So all the answers are good. Fortunately, no one said, 1 million or 1,000 or something. It's obviously lower than that. All right. If you were to flip a fair coin 6 times, which sequence do you think would be most likely?
The second one?
The second one, okay. Anybody else have any ideas? The most likely sequence. This is a fair coin 6 times. We have one person saying number 2 is most likely. Nobody else? Okay. So here's the hint. Each of these flips of the coin are independent. And if it's a fair coin, what do you think the probability of getting heads or tails is? Anyone? Come on, somebody must know the answer to this.
Aren't
What's
they
it?
all the same likelihood?
Well, what is it?
It's 50% for heads or tails.
Right, of course. So if it's a fair coin, you flip it once, the probability is 50% or half that it's heads, or 50% or half that it's tails, of course. So if these are independent, what was that rule that we learned from chapter 14? Was it the addition rule or multiplication rule about independent events? I remember what we do. Do we multiply, or do we add probabilities?
Multiply.
Multiply, of course. So does it really matter whether it's heads or tails here? They all have the same probability. No, it doesn't matter. So it looks as if number 2 is more likely, because number 3 looks like, hey, there's not much of a chance that happening, getting 3 heads and then 3 tails in a row, and then getting 6 heads in a row. That definitely is not, that seems to be highly unlikely. But in essence, if these are independent flips of the coin, six times, then each of these probabilities, all 3 of them are going to be the same probability, which is 1/2 to the 6th power, right? 1/2 multiplied 6 times would be the answer. I think that's 1 out of, what is that? 1 out of 64? 1 divided by 64. That's the probability of each of these. Each of those. So what happens, I think, and the reason why, I'm sorry, who answered the second one? Who was it? Maybe you don't want to answer who we were.
Me, Jackie.
I said the 50.
Jackie. No, it's okay. It's
I said
okay.
50 people.
I just said that because it looked like the first one was not likely because it's all heads, and then the other one was like too cut and dry. So the middle one just seemed like,
Yeah. And that is exactly what most people would think. All right. Most people would think that it's the middle one. I would say, I bet you if you ask this question to people who are not studying statistics, I would say 70–80% of the people would say the middle one. And yet, we know from chapter 14 that each individual flip of the coin is independent of every other flip of the coin, and that the probability of getting heads and tails is exactly the same. So it doesn't matter whether it's heads or tails. These 3 probabilities are equal to each other. But what you're bringing out is, Jackie, what you're bringing out is that by just visually looking at these 3, it seems as though number 2 is the most likely. Okay? It seems as though it's the most likely. And that is a very prevalent observation. But it's not true. And the point of chapter 17, if you get anything out of chapter 17, is that sometimes our perceptions and observations mislead us to give us the wrong probability. Or if we're comparing different events, we're ranking them incorrectly. Okay? So our intuition, our perception, our brain, the way our brain works, all of those things sometimes work against us when we want to accurately assess the probability of an event. Okay? In reality, these 3 are equal. Okay, so, all right, here's number 5, question 5. This has to do with expected value, all right? But forget about the expected value idea. Take a look at these pairs of choices here. You have A versus B, and you have C versus D. So A's choices, you're given a guaranteed $240. B, you either have a 25% of winning 1,000, and well, let's say you have a 25% winning 1,000, or there's a 75% of getting nothing. Okay. Now, forget about what we've studied. What do you think? Which one would be preferable to you, A or B?
A.
A. Again, 70 or 80% people would say A. Why? Because well, go ahead. Tell me why. Why would you pick A?
Because you're guaranteed to at least get something.
That's right. The guarantee idea. The guarantee idea. Now, C and D. Sure loss of $740 or a 75% chance to lose 1,000 and a 25% chance to lose nothing. Which of those two would you prefer?
For the B or just for
C or D? C or D?
D.
D. Again, 70 or 80% of people would choose D. For the same reason, except it's reversed, right? You would say you'd want to avoid a sure loss. Is that your reasoning? I don't mean to put words in your mouth. But.
Yeah, but looking at B again, the 75% chance of getting nothing is actually better because it doesn't say anything about losing.
Oh, you mean in A and B? Yeah.
Yeah, but yeah, D for the second one.
Yeah, yeah. And that's exactly what most people would choose. All right. So don't feel bad that this is, but in terms of long run expected value, remember the constant of expected value, the long-term average of repeating this over and over again, the answer should be in B, between A and B, the answer should be B, not A. Because if you multiply the probabilities times the values, 25% of 1,000 is $250 and 75% of 0 is 0. If you add those two products, you get $250. So over the long term, B is the better choice. C and D, C is the better choice here. Why? Because again, using expected value, 75% of 1,000 is $750 loss, and 25% of 0 is 0. So when you add up the expected value, you get negative 750, or a loss of 750, and certainly a $740 loss is less than that. The C is better over the long term, but most people don't consider long term when they make choices. So they would actually predict or pick the other choice in both A and B and C and D, because at first glance it looks like better. You want a guaranteed benefit, and you want to avoid a guaranteed loss, and that's the way our brain is wired. We're wired this way. So again, thank you for your answers, because it gave me exactly what I wanted: the perceptual answer versus the what we would call the logical answer, if you want to call it logical. The what a computer would give us as the answer, right? Computer would be unemotional and would just choose A and C as the answers. But we are humans. We have our particular way that our brains are wired, and we pick the opposites. Okay. So let's move on to slide. So remember from, I guess it was the last chapter, they talked about, or maybe it was chapter 14, where they talked about the difference between relative frequency interpretation and personal probability interpretation, all right, in terms of probability. Relative frequency interpretation is based off actually repeating an experiment over and over again and seeing what you get. Personal probability has to do with what? It has to do with your own belief system, right? And many times people don't consider the relative frequency interpretation at all. They're influenced by other types of things that take people away from that relative frequency interpretation. Coincidences, right? Can somebody win the lottery twice? You know, one person win the lottery twice. Well, over many, many, many tries, it's possible. It would be highly unlikely, I mean, extremely unlikely if somebody bought a ticket 2 separate months and won both months. I mean, it can happen, but there have been cases more recent than the one they're showing here in 1986, where somebody won a big lottery twice. But it's more likely, if you consider it over a longer period of time, that somebody somewhere is going to win a major lottery twice. It's happened and it will happen again. Now, the low probability is that somebody buys 2 tickets, you know, 1 month they buy a ticket, the next month they buy a ticket, and they win both lotteries. That would be incredibly unlikely. But in terms of over time, it's possible. It's possible to find people who won it twice. And it's more likely if, you know, there's been, you know, person plays all the time, plays the lottery all the time. So coincidences occur more frequently than people think. All right, so what they're saying here is what's not improbable is that someone somewhere someday will experience those events or something similar. So they say we're really asking the wrong question when we say, can somebody win it twice? If there's a 1 in 17 trillion probability of winning it once, of winning it twice, what they're really saying is that there's one person to win it exactly twice, exactly both times they played. But again, people play this many, many times over many days, weeks, years, and there will be people who will win it twice. And the probability that we'll find somebody who will win it twice is actually not so bad compared to the 1 in 17 trillion. These researchers found it was more like 1 in 30 chance of a double winner in a 4-month period. And better in even odds, that means better than 50% chance that we would have a double winner in a 7-year period somewhere in the US. So it really depends on what period of time you're looking at and how many people you're looking at and how often do they play the games. All right, so here's the answer to that question. I think we ended up with 30, 50, and our person who said at least 365, the safe choice. The answer is 23 people. Typically, we ask when I've done this in the past, I've asked the question a little bit differently because I want people to actually do the calculation. I'll ask if we have 23 people on, let's say, on a field, maybe they're playing some game and there's 11 on one side, 11 on the other side, and 1 referee. What's the probability of at least 2 of those people on the field having the same birthday? And the answer is a little over 50%, 50.7% with 23 people. So 23 people is sort of like the minimum number of people where this probability breaks past 50%. Now, how do you calculate it? Well, you're not responsible for this calculation, but think about at least 2 people sharing a birthday. We would say that probability, remember, probabilities are between 0 and 1. So the probability that at least 2 people share the birthday would be the same as saying 1 minus the probability that no one shares the same birthday, right? And so it's easier to calculate the probability that no one of these 23 people share the same birthday. So what do we do when we do the calculation? Well, the first person, if we just pick the first person out of the 23 people, how many different birthdays can they have? Well, they can have 360. Let's assume this is not a leap year. They're going to have 365 possible days, right? One of those 365 days is their birthday. Then let's say we pick person number 2. Now remember, we're going to first calculate the probability that none of the 23 have the same birthday. So if the first person has a particular birthday, that second person has only 364 birthdays to pick from. All right. So the first person's probability is 365 divided by 365. The second person's birthday is 364 divided by 365. The third person's birthday, as you can guess, decreases by 1 again, is 363 divided by 365. So if you take those probabilities for those 23 people and multiply them out, you will get 0.493 when you use your calculator. And since that's the probability that none of the 23 people share the same birthday, 1 minus that number gives us the probability that at least 2 people share the same birthday, which is 0.507, or a little over 50%. And that's how you figure it out. But most people overestimate the number of people. Now, the person said 30, that's a pretty good estimate. Usually when I ask people, I hear numbers in the thousands or even in the millions when I ask this question. So all three of you, I congratulate you. You did a great job in getting very close to the answer, getting pretty close to the answer. So the answer is 23 people. All right, any questions about that? So that's where people tend to get, they tend to underestimate the probability, right? It says most coincidences only seem improbable, only if we ask the probability of that specific event occurring at that time to us as individuals. They seem improbable, but they're more probable if we consider it over time with more people, things like that. Now, this is another one called the gambler's fallacy. Now, I don't know if any of you are, you don't need to admit this at all, but any of you like playing games of chance. A gambler obviously plays a lot. Obviously, it might be considered to be an obsession, but people think, and this is the key to what's called the gambler's fallacy. People think the long run frequency of an event should apply even in the short run. Okay, so they think they see just a small number of cases, and they think, for example, if you're playing some game in Atlantic City or Las Vegas, wherever you are, and you're having a losing streak, you know, you might think, all right, it's time for the winning streak to happen. You know, the law of averages will take me back, but that doesn't really work that way. You're still in a short run, you know, mode, and it's possible that losing streak, that so-called losing streak, could continue for a while. So people tend to think long run is something much shorter than it really is. And they use small samples to represent this. All right. And then they, you know, in the book, they talk about this particular example. They're looking at 3. This is again, this is similar to what we were looking at before. And let me see let me look at the next slide here. So again, we're looking at tosses of heads and tails. And again, like, I forget who answered the number 2 here when we were looking at this before. They tended to look at this sequence of heads and tails, this one here, to be more likely than the others because they looked to be less likely, right? I think they were all heads, and then 3 heads, and then 3 tails. And the reason why you think they're less likely is because you're thinking long term when you should be thinking short term. Many times, randomness, just random events, have little runs associated with them, such as, you know, 3 heads followed by 3 tails. We consider that to be unlikely because it seems like, hey, that should, you know, randomness should be more mixed up, right? More, you know, heads followed by tails and things like that. But in the short run, we will see runs, things that look like runs that should be, you know, we might consider unlikely, but they are random events. You could see 4 heads in a row followed by tails and another head. We might think that's highly unlikely. But again, it's only 6 throws of the coin, 6 tosses of the coin. We would expect more of a 50-50, right, between heads and tails. But after 6 throws of the coin, it's not enough. We need many more, maybe hundreds or even thousands of tosses of the coin to see that overall we'll see 50% heads, 50% tails. And even there, we'll see some runs. So these streaks or runs they happen naturally in random events. They just happen that way. And you have to be very careful in making assumptions about randomness, with small samples. I mean, if we saw, like I said before, 6 heads in a row, you might say, hey, that's highly unlikely compared to 3 heads and 3 tails or this one here. But it's not. It's just as likely to happen over the short term as these other 2 events. Okay. The other thing that people tend to think is this idea of memory. A gambler, an obsessive gambler, tends to think that there is memory. That is somehow the gods or the laws of chance. If you've had a bad streak, it's got to be turned around sometime soon, right? There's some memory there. There's some memory that, well, there hasn't been any luck so far, but the luck is coming. And independent events have no memory. Actually, mathematicians talk about memory in terms of probability. They do say independent events have no memory. That is, what's just happened doesn't influence what's about to happen. That's what we mean by no memory. Okay, see what time it is. All right, we still have time. So this gambler's fallacy, this idea of runs, all right, basically applies only to independent events. Right? Well, let's read through. No, I think we already said what gambler's fallacy is. Okay, but it only applies to independent events because independent events have no memory. But if we do have dependent events, then the knowledge of one outcome does affect the probability of the next one. Okay, and therefore the gambler's fallacy doesn't apply in that case. It is possible. And what's an example of that? That probably a game like that, and would you play? What's that game with getting to 21? What's that game called again? Anybody know that game and play for cards and you're trying to get as close to 21 without getting over?
Blackjack.
Blackjack. Blackjack is a game that's not dealing with independent events, are we? Because there's typically 3 decks of cards, and people who are good players have good memories, right? They remember what's already out, and they're trying to figure out what the next card is. So that's a game where it's not gambler's fallacy. And that's why, of course, on blackjack tables, the casinos are they have cameras all over the place. They want to make sure somebody's not using a computer or using some system to count cards, because it does put you at an advantage. So that game has memory. And so what's happened is not independent, but what's going to happen is not independent of what happened in the past. A roulette wheel, it would be an example of independence, right? When you spin the wheel once and then spin it again, what you see is independent of what just happened. Okay, any questions about gambler's fallacy? So gambler's fallacy is that the idea of runs, right? That you're applying something over the long term that to the short term, the idea of runs. Okay. Now this one's a little more complicated. It's called the confusion of the inverse. So this deals with, typically deals with medical tests and things like this. So here's an example here. Patient has some sort of lump, and a doctor says that it's 1% chance that it is malignant. In other words, 1% chance that a person has cancer. All right, so the lump, let's say lump in the breast, person gets a mammogram. Now it says here mammograms are 80% accurate for malignant, for cancer, and 90% accurate for non-cancerous tumors. All right. So a mammogram, suppose a mammogram indicates that a person has cancer. What are the chances it is truly cancer? So you can even ask this question to doctors themselves who may not be familiar with the actual calculations. They might say, all right, you got a mammogram test. What's the chance that the person really has cancer? And they'll say, 75, 80%, something like that. The answer actually is 7.5% based on these numbers that are given up here. Now, this course doesn't teach this formula called Bayes' theorem. Bayes' theorem is a way of calculating this probability here. Now, I'm not going to teach it, but the answer is 1/10 of what most people would answer. Most people would think, you got a test, a mammogram, and what's the chance that, and it shows that you got a positive result, right? Positive meaning, not positive in a positive sense, but positive meaning the test turns out that you have cancer. And person thinks the mammogram's got to be pretty accurate, so they're going to say 75, 80% accurate. But the answer is only 7.5%. So here's the deal, that the doctors were answering the revert, were thinking they were answering the right question when they were actually answering the inverse of what they wanted to know. What they really wanted to know was, what's the probability that if the person has cancer, that they would get a positive mammogram? That's really the probability that they're interested in. Okay, and that is, anybody know the answer to that question? So what is the probability of having a positive mammogram given that they had cancer? Well, the answer to that is 80%. It's given in the problem there. Oops, sorry. That's that probability. It's given right here. It's 80%. All right. That's the question that the doctors are interested in. All right. Given that they have cancer, what's the probability they would have a positive mammogram? Question that's being asked is, what's the probability that if you have a positive mammogram that you have cancer? So this is asking the reverse, isn't it? And that's where the 7.5% comes in. You have a positive mammogram, what's the probability that you actually have cancer, not knowing it? And the answer is 7.5%. So what do the doctors who know this, what do they have to do? They have to do more tests, right? Because a mammogram is just giving them an initial result. They know that there's only 7.5% of cases where if you have a positive mammogram that you have cancer, so they have to do some other testing, right? They have to do some blood work or whatever they have to do. All right, a biopsy, right? Biopsy is probably what they need to do. All right, now let me see if they say it here. Yeah, here's a table that sort of explains it. Suppose we have 100,000 women, right? 100,000 women with a lump on their breast. All right, so that everybody here, all 100,000, have this symptom. Now, go back. Let's go back to what these numbers mean. Mammograms are 80% accurate, right? For cancer, 90% accurate for benign. Let's now look at it. So it's 80% accurate for cancer. So suppose we have in this, out of this 100,000 here, okay, we have 1,000 people who have, they find that have cancer. 1,000 have cancer. 80% of that is 800. Now, how did we come up with 1,000 here? Let's go back. 1% of the population who have these lumps have cancer. So if we have 100,000 people, 1,000 of them will have cancer. So that's where they come up with this. That's where the 1,000 comes from. Out of the 1,000 people who have cancer, or excuse me, have cancer, 800 of them have a positive test, right? That's the 80%. 80% accurate for for cancer. 80% accurate. What does that mean? That means out of all the people who have cancer, the test shows 80% of them. Okay, it's accurate. So it's showing 800 of them showing cancer. 200 of those people showed the opposite. The test showed that they didn't have cancer. Now, everybody else, there's 99,000 people who don't have cancer, right? Because 1% do, 99% don't. So that's 99,000 out of 100,000. Now, what did they say? They say these tests are 90% accurate for benign, which means the test is going to be negative. The test shows benign, right? That's what they mean by accurate. So 90%, 9.9 times 99,000 is 89,100. Which means the test made a mistake in 9,900 times out of 99,000, because 99,000 minus 89,100 is 9,900. So in 9,900 of the times, okay, in 10% of the times, the test was wrong. It says that the person had cancer when they didn't. So let's go back to the original question. Now if you just total everything, total the rows, total the columns, you get these numbers. Go back. You want to know if person has cancer, what's the probability? Probability that excuse me, the mammogram indicates a lump. All right. So the person has a positive test. What's the probability that they truly have cancer? That's what they're saying here. So they have a positive test. Positive test is this column here. 10,700 is the total. What's the probability that they actually have cancer? There's 800 of them have cancer. 800 divided by 10,700 is 0.075. This is one way of proving that number, coming up with that number. A little complicated, but you could see, I mean, this result might surprise you, right? It might surprise you. What's the probability that if you have a positive test that you actually have cancer, you would think a higher number? It isn't. It's low, 7.5%. All right. So this is called the probability of false positives. Probability of false positive. If the base rate of the disease, now what's the base rate for the disease? That's that 1% of the population that has cancer, if they have a lump. The base rate of the disease is very low, 1% would be very low. And the test for the disease is less than perfect. There will be a relatively high probability that a positive test is a false positive. So what's a false positive? False positive would be a person who got a positive mammogram, but they don't have cancer. And what is that rate here? It's 9,900 divided by 10,700, right? 92.5%. Right? So that's the probability of a positive test being, so that's called a false positive. So the base rate is that initial probability. Okay. Now these two terms here, you don't have to memorize it because you have it in your book, but let me explain what they mean. You have a test like this. One of them is called the sensitivity of the test. It's the proportion of people who correctly test positive when they actually have the disease. They test positive when they actually have the disease, right? This number here. They test positive when they actually have the disease, right? So that's 800 here out of 10,700, right? That is called the sensitivity of the test. Okay, so that's what we calculated before, 7.5%. The specificity of the test is the proportion of people who correctly test negative when they don't have the disease. Here are the people who test negative, who don't have the disease. Well, that would be the 89,100 out of the 89,300. That proportion there is called specificity of the test. All right, so there you go. That's kind of complicated. That's the most complicated part of this chapter. But people who are getting into any sort of medical part of their life, medical career, be good to know this sort of thing. And then they talk about streak shooting and so forth in this case study. You can read through it. And then they talk about expected values. We talked about this earlier in these cases here. All right. We talked about, that people would pick A and would pick D, and B and C are the better choices in terms of expected value. However, if you look at this situation, this is the last thing we'll talk about before a quiz. We get different answers here when the numbers are dramatically different. Okay. And we have small probabilities and large possible sums. Here's a case here where if we have a choice between a 1 in 1,000 chance of winning 5,000, like a lottery situation, or a sure gain of $5. Now remember, in the previous case, we would go with the sure gain, right? But remember, the amounts here are very similar. 240 versus 1,000, there's not too much of a difference in the numbers. But if the numbers are quite different, and there's a very low probability of winning the bigger sum, then people tend to go with what? Going after the bigger sum. That's why people gamble. That's why people buy lottery tickets. The expected value of alternatives A and B are exactly equal to each other. All right, in this case, because 1 divided by 1,000 times 5,000 is $5. So and we're not considering in this case, the amount of money to pay to play the game, but in this case, the two are equal to each other. And yet people would go for A for sure because they have a chance to win $5,000. And $5 is, very small amount. Most people don't go for the $5, they'll go for the 5,000. So in this case, people will take the chance and try to win 5,000. How about this case here? A 1 in 1,000 chance of losing 5,000 or a sure loss of $5. Well, $5,000 loss sounds crippling compared to losing $5. So people are going to choose C in this case because of the big difference between the dollar amount, between 5,000 and 5. But the expected losses are exactly the same. 1 divided by 1,000 times 5,000 is $5. That would be your expected loss. All right. So the answers here tend to be different than the answers in the previous problem just because of the big differences between the dollar amounts. People want to go for the bigger gains and they want to avoid the large losses even if the chance of losing that amount is small. By the way, warranties on like cars or big ticket items, they try to sell you on the idea of buying a warranty because of the large amount of money, and they'll say, oh, it only costs some small amount of money. Well, they forget to tell you that the probability of losing of that part of the car, whatever that the warranty's on, the probability is very small that event's going to happen. So warranties make people go for alternative C, and lotteries would make people go for alternative A in this case here. The previous example there's no lotteries involved here. There's no warranties involved, and people tend to people should go with B and C, but they go with the opposites because they look a little bit better. Okay. Any questions about what we went over? I think it's time for, and then this last one here also has to do with the idea of people tend to underestimate or overestimate probabilities. When you bet on things like the British Open or whatever Super Bowl, the house, the so-called betting organizations tend to make money, and what they do is they increase the probabilities of these things occurring so that they can make money off of them. I could show you the math behind it sometime, but that's what this last case study is all about. All right, so we'll stop sharing on this, and it is 2:50 right now, so it's time for your quiz. Just thumbs up if you see your quiz. Yes, I see a thumbs up. Great, good. So you can start again. This is 20-minute quiz. Good luck, and send me a chat if something in the chat if there's some issue.